we're gonna wrap up a little bit what we were doing yesterday, and this is this model of online learning with experts. So let me recap a little bit. We had this algorithm hedge, and hedge used this notion of loss, cumulative loss actions. And then we had the weights that were proportional to e to the minus cumulative losses. Okay, and then we had the normalization constants for the weights. And finally, the probabilities, they were just the normalized weights. So now, we had an equation that gave us a bound on the regret. So let me recall a few things for you. So this was the best action at horizon t. Okay, and we defined the regret as the sum over time, the sum over the actions of the probability of playing the action at time t, the loss of the action at time t, minus the cumulative loss of the best action. And we showed that we could bound, in general, this by something relatively simple. That was the log of the number of experts divided by the learning rate plus the learning rate divided by 2, sum over t, sum over I of LTI squared and PT sub I. Okay, so what we argued is that, okay, this inequality actually, it's interesting to note, because up to this point, in order to prove this inequality, we just used the fact that losses were non-negative. This is the only fact that we use to prove this inequality here. Then, if actually losses are bounded between 0 and 1, I'm not using the universal quantifier over t and I here, they are understood, then we could do the tuning, we could upper bound this quantity here by 1, do the tuning for eta, and get the bound on the regret which we showed. I'm just disregarding small constants here. That was this one. And this was the bound that held when you had the full information, in the sense that after each prediction, you saw the losses of every action for that time step. So now we want to do this in the bandit setting. The bandit setting is the one for product recommendation or online advertising, which we mentioned at the end of the class yesterday. So in the bandit setting, things are much harder because, let me just recap it for you. Things go like this. So we draw our action from the probability distribution, right? Then we pay our loss, the loss corresponding to the action we chose at that time step. We observe what we pay. So in other words, we observe the feedback of the user for the specific product we recommended, or for the specific ad that we showed to that user. And then we do our update. Okay, PT goes to PT plus 1. All right, so the bad news here is that we cannot run hedge anymore. Why can't we run hedge anymore? The problem is we cannot compute. We cannot compute this cumulative losses for single actions. Why can't we? Because these losses are observed at any time step S only when we play that specific action, when we selected the specific action I. So at every time step S where we don't select I as IT, we won't observe the loss component for I. So we are stuck and we have to come up with something. So the idea here is that we do something which, if we were in a statistical setting, would be obvious. We try to estimate these losses. So we replace LT of I with estimates LTI hat. All right, so how can we estimate, right? Well, there is some probability here. There is some probability because we are drawing stuff according to our own randomization, no? We are using a randomizer predictor, and there is some randomness there that we use to draw actions. So we can use this randomness in order to come up with a wise estimate. And there is amazingly easy estimate, which works very well, and this is called importance weighted estimate. This is a super easy but extremely effective. The idea is, all right, let's see. I want to estimate the loss of action I at time t. Okay, there are two cases. Either I do play action I at time t. In that case, I do observe the loss of action I at time t. So I can definitely use this information. Okay, let's leave some little space here. Otherwise, if I don't play, I don't observe anything. So what can I do? Maybe, I'm optimistic, I put 0 here. So whenever I don't observe a loss, I assume that the loss is 0. But then somehow I have to compensate for the fact that every time I didn't play that action, I was optimistic. And I compensate by dividing the loss of the observed action by the probability of playing it. Right. So since I divide by the probability, I'm making the loss bigger, right? And this should compensate the fact that whenever I don't observe it, I make it smaller, because 0 is the smallest possible loss. Okay, so now I will call XP3 the algorithm hedge run with these importance weighted loss estimates instead of the true losses, which I don't observe. Okay? And XP3 is an algorithm that was introduced in the mid-90s. It stands for exploration exploitation with exponential weights. Okay? So the idea is that because you don't have this full information about the losses, sometimes you have to pick an action in order to find out what is its loss, even though maybe the action is going to be kind of bad. Wonderful. So what are the properties of this loss? So first of all, we have to notice that now these probabilities are random objects because the L hat Ti depend on IT. Now, probabilities depend on losses, and losses depend on our own random actions, according to this estimator here. So, right? So, I will be using probabilities that will evolve as a random So not true anymore that my probabilities follow a deterministic a trajectory in the simplex, but they will follow a randomized trajectory, depending on my own randomization, all right? So let's see properties of these things. Okay, first of all, let me do something, let me understand how can I use the hedge analysis. Can I recycle the hedge analysis here? Okay, yeah, actually, you see, these things are random, but if I fix, suppose I fix a sequence of realizations for the actions. So now the PTs are deterministic because I determined all the random outcomes. They are function of, so they become deterministic. So now I can really apply the hedge analysis on these quantities because everything is deterministic. I can have these things here. So I just have to adjust the notion of regret. So how is regret? Let's call it this way. So regret is now, I define it using the L hats instead of the L. Okay. Yeah, I'm getting there. What?
Can you repeat the problem statement one more time? Because it just lost track a little bit. So can you repeat what is the problem we're solving?
This is the problem it's a bandit problem. Is the problem we are solving is this. So we want to bound regret when we don't observe the entire loss vector at every time step as we did yesterday, but we only observe the component of the loss vector that corresponds to our own play.
I see. So you are saying that yesterday, at every moment, we observed the entire vector for every possible action?
Before we could update for every possible action. Now we can only update it for the action we actually chose. So we have to replace, we have to put some placeholders for things we didn't see, and our placeholder will be 0.
But I still do not assume anything.
We don't assume anything. Everything is worst case as before. This is, thanks for your question, because it's useful, I think. Partial information about the loss vector. One component instead of k. So that's what you're missing. Okay. Right. So please do ask questions. So now, as I said, so I can define. Hello. Okay. And then I can take this bound, which I said holds for non-negative losses. These L hats are non-negative losses. So I can just use this bound, basically redoing the analysis I did yesterday, replacing the L's with the L hats, and explaining the fact that the L hats are non-negative, so the analysis works. So now I can write this bound here, just by redoing the same analysis I did yesterday, and what I get is ln of k divided by eta, this is unchanged, plus eta halves, sum over t, sum over I, and what? I have LT hats I squared PTI. Cool. So it's formally correct. It doesn't mean much as so far, but I just used the algebra I developed yesterday. I just used the algebra, and formally I can definitely write this inequality. It doesn't mean much. I just fixed anything random. So this is just a formal algebraic relationship between R hat and this other quantity here, which is an upper bound. So now, all right, now I want to exploit the fact that I have randomness. So I should be taking averages according to these ITs. These are my random actions. So I should really take expectation with respect to the random actions I made and see what happens here. Okay, in order to do that, okay, let me define ft minus 1 is sigma algebra induced by the 1 I t minus 1. So this is the sigma algebra of the previous of all the choices, random choices made by the algorithm up to time t minus 1. I will use this for conditioning. Okay. So now let me do a very simple computation. Let's look at the conditional expectation of a loss estimate at any given time t and for any action I. I'm conditioning on the past. So how do I do this computation? Okay, that's super easy, right? Let's look at the definition of these things. Oh, it's up here. Okay, so these random variables has, so I did the conditioning. Why did I do the conditioning? Because of I is determined when conditioned f. So if I condition on the past random choices of the algorithm, the probability becomes determined. Indeed, I use this probability to pick the t action, right? Each time I pick a new action, I update my probability because I know the realization, I can compute the loss estimates. Therefore, Pt is determined in the conditional space of the first t minus 1 random draws of the algorithm. I get some deterministic quantity which I can use as a probability. So now let me do this. Okay. So this random variable has two values. So has value LTI divided by PTI with probability IT equals I conditioned on f t minus 1. So if I pick action I, then my estimate I will have this value. That's all right. If I don't pick action I, my estimate I will have a value 0. It's here. That's what's written here. So this is a computation, no? Okay. So what is this? This is exactly the probability of drawing the action I at time t by definition. By capital sub t. Okay. I draw action I sub t with that probabilities. Therefore, I can simplify this and I get that hat is an estimate of my true loss. And this is the trick that the importance weighting buys for you. And the cool thing about it is that I'm just using the internal randomization of the algorithm. I'm not making any assumption about the outside world. So loss vectors are still completely in the, it's a deterministic process, okay? And I'm just using the randomness of the algorithm in order to come up with unbiased estimates, which is kind of cool. The first time I saw it, I said, wow, this is quite amazing. Okay, any questions here? Yes? No, it's conditioned. I conditioned it on the past. The past matters, yeah. The probability, as I said, you compute the probabilities based on the past realizations. So if I fix the past realizations, I have a probability, my probability becomes a deterministic quantity. So I can write it outside of the expectation. Okay, thanks for all these questions that are helpful, because I'm not saying everything, so you should. Okay, so now let's see how can I information. Well, I can, for instance, I can compute the expectation of this of RT hat defined here. Okay, I want to compute the expectation of this quantity here. Okay, so this is going to be the expectation of sum over t. And I can definitely write the expectation inside because I can use the Tower rule for expectations. Oh, I forgot a sum over I. I'm very sorry. So I was too hasty. There's a sum over I here, which I forgot. Please go back and amend. Okay. So I will write it here again. So there's a sum over t, sum over I. Sorry for the mess. And then I have the conditional expectation of LT hat of I, PTI. And this is a conditional expectation. I'm becoming sloppy. Okay. And then I have the other part, which is minus, and this is the other part of the is this part over here. So I can also do the expectation, sum over t, expectation of LT hat KT star, conditional. Okay? So now I'm using the fact that these conditionals are actually the true thing, right? This we just showed it. So now I can write in a cleaner way sum over t, sum over I, LTI, PTI, minus, all right, and this is a completely deterministic quantity because it's just are just the losses of the best action, and everything is deterministic on this side. Okay, so this is fine. This is the regret, right? Why is it regret? But well, we can, if you want to see it, you can write this part here as a sum over t, and then LTIT. So this is the expected cumulative loss of the algorithm itself, and this is minus the expected cumulative loss of the best action. And this is our notion of regret. Okay, so it's fine. If we take expectation of this quantity here with respect to the random actions of the algorithm, we get back the regret we are interested in. The difference between the cumulative expected performance of the algorithm and the cumulative expected performance of the best action. Very nice. So now we have to deal with the upper bound. Okay. We are now looking at the right hand side here. So now we can write ER hat T bigger or equal than, okay, I have two parts here. This part here is completely deterministic, so that's fine. I just write it. And now this other part over here, it contains L hats and P. Okay, so I write it in a proper way. And I'm almost done. Yes, thank you. Sorry. Sum over T, sum over I, E, LT hat I squared, FT minus 1, in the PTI. That's it. Okay, so now you see the term I'm still missing here has to do with the second moment of my estimates. Yeah, I mean, my estimates, you know, I need my estimates to be unbiased and to have a small variance, a small second moment, to control the second moment of my estimate. How do I control this second moment? Okay, so let's focus on this term, and this is super easy also, because I just essentially to check the unbiasedness, and this is super quick. So let's take a look. Okay, this is going to be, whoops, okay, the square of what we wrote before. Okay, and then I have the probability that IT equals I, conditioned of 1, which looks like 0. Okay. Now, as did before, I notice that this is like Pt.2, and then I'm using the fact the original losses are bounded between 0 and 1. Losses are truly bounded between 0 and 1. So I can upper bound this. At the end, I can simplify one of them with this. And then I can write it as 1 over Pt sub I. Okay? So now, look at that. So the second moment of my randomized estimate is upper bounded by the reciprocal of the probability. Okay? So now I can go back and plug it back there. And what I get is something nice. Sum over t, sum over I, 1 over Pti times Pti. Oh, wow. Yeah. So I can cancel this with that. This cancellation is so pleasant that it got a name. It's called the bandit magic. Bandit magic. Bandit magic is when the variance of your importance weighted estimates are nicely controlled because of this strange interplay between the probabilities and the variances. Okay, so now these are ones. How many times I'm summing these ones? K times and T times. So T times K. So at the end of the day, I get that this is at most ln K over eta plus eta halves KT. And yes. Okay, so that's it. We've gotten a bound on the regret, which depends on eta. So now everything is left is to choose eta. Okay? So now, if you allow me, we choose eta. And if we choose eta of the order of square root of k ln k divided by t, we get that the expected regret of our is bounded by constant, there's like a 2 constant somewhere, kt ln k, and that's the bound for the bandit case. Okay? So notice that with respect to what we had before, so what we had before is this. So what we got is a k term inside a square root. And the k term is there because we are seeing a kth of the information. So this is the price of the variance that we pay because we see a much smaller amount of information. So before we didn't have any variance, now we're going to have a variance which is the order of k because we are seeing 1/k of information as with respect to before. This is all the intuition. Okay? You can definitely play the tricks we did before, and you can choose eta t of the order of k ln k divided by little t, and have dynamic tuning as we did in the previous case, and we get this bound for simultaneously for all horizons capital T. Okay, so there is no much issue in tuning, in the tuning for a specific horizon, because you can choose this dynamical tuning and things will work out with a bit more math around. Okay? So that's nice. And any questions up to here? So, yes.
You admitted also that LT needed to be between 0 and 1.
Yes.
And you have this right here when it's like LT over PT?
No, the L hat, I don't need any bound on L hat because, so the original losses are bounded between 0 and 1. The L hats are don't have any upper bound because they're definitely bigger than 0. They can be as large as they want because we're dividing by probabilities, and this probability is very small. However, the bandit magic is saving our ass because I canceled that p in the denominator. I just canceled the p in the denominator. That saves my yes. Yes. Otherwise, I would be hit by a huge variance. But amazingly enough, the thing worked. The case? The K. This is a number of products. Yes. Yeah. So because our probability is the support of our probability distribution, the size of the support. Yeah. Yeah? No. The old previous realizations of of the algorithm's random choices, which you have because you run the algorithm, you see what the algorithm chooses. So. On all of them. All of them. So you're running the algorithm at time t, you know what the algorithm did up to time t minus 1. So you can, so that's the reason of the conditioning. The conditioning up to time t minus 1 means that you ran the algorithm, so you have realized those random variables. So at time t, you are in that conditional space. Things happened, okay? So you can compute your probabilities. Otherwise, you won't be able to. Okay, so now let me take a little twist because I decided to do this little detour, but this is really, I think it's fun. So let me look at the way, at the following idea. Okay, so you might say, okay, maybe in some cases things are not so extreme, right? So we have two settings. This expert setting in which you get the entire information about the loss vector. You know what the users would have responded to all products. And then you have this super bad case in which you get only one component. How about a case in which actually there are some relationships between actions? So maybe, your products are cars, and you know that if a user liked a certain car, he would have liked also that other car. So you can actually have the similarities between actions allow you to infer what the user would have said if you had recommended a similar action. Okay? So how can we model that? So let's see, we have a similarity graph over actions. These things exist, so Amazon has a similarity graph of products, and you can imagine that you can do it. So now you view your actions like, maybe you have some set of actions, and you have like a similarity graph that is telling you that these actions are all actions connected by an edge. So edges indicate pairwise similarity. Okay? So, for instance, in practice, what it means that if I choose, let's say, if I choose a specific action at time t, I observe LT of IT as before, but then also all LT of J for J such that is in the neighborhood of yeah. So the similarity graph, I indicated V is the set of actions and E is the set of edges. So now I can define this neighborhood of I. So the neighborhood of union all the nodes J in V that are connected to I. So again, if I pick this action, I'm going to suffer this loss, but I also observe the losses of this guy, and this guy, and of course the loss of this guy. So I pay the loss of the action I choose, but I observe the loss of the action I chose and also the losses of the actions in the neighborhood of the action I chose. Because they're similar, I can infer, okay? All right, so how does this change things? So first, let's see if we did generalize things. Okay, so in the expert's case, G is a click. Whichever action I pick, I always observe everything. So G is what? G has no edges. Okay, because I only see the loss of the action I pick. So I can now interpolate, using this notion of similarity graph, I can interpolate between these two extremes. Either I see everything, I have full knowledge of my decisions, also those that I didn't take, or I have only the knowledge of the action I take. Now I can interpolate, and this graph will tell me the communication pattern that my learning process has at its disposal, right? The learning process can rely on this communication pattern among actions. Now you can imagine things like, maybe this action has a high degree, so I should pick it more often than the others, because every time I pick that action, maybe I incur in a big loss, but I know a lot. Because this action has a big neighborhood, so I know the losses of all the actions that are similar to that. So you may imagine there are some nice trade-offs going on here, okay? So how do things change? How does the game change if we do that? Well, actually change very, very little, because we can take all the ideas we have already seen and just generalize them a little bit, but very, very little. Something nice will come up out of this generalization. So let me work this out for you. So now so here you have this neighborhood, which is the action, the neighborhood of I contains I, and all the actions that are connected, adjacent to I. Fine. So now I'm gonna change my loss estimates. I'm still using loss estimates, but now I can do something different. So let's write it like this. LT sub I divided by Q T of I, which is a quantity that I'm going to define, and then 0. So this is when I observe the loss. When is that I observe the loss of an action? Okay, I observe the loss of an action whenever the action I choose is in the neighborhood of that action, all right? So whenever IT belongs to the neighborhood of I. So if I pick I or an action which is adjacent to I will observe the loss of I because of this observational model I just assumed. And if I don't observe anything, I will just put 0 as before. So what is this Q? Well, in order to have my unbiased property estimates, I should set Q as the probability exactly of this event conditioned on the past. All right. Okay? So this is something I can actually compute. I know the probabilities with which I pick the actions, so I can sum them up over a neighborhood of the action I actually chose. I can definitely do that. Okay? So now it's very, very easy to redo those computation for the unbiased estimate and for the second moment. Okay? So I don't do it, I just write it here because it's exactly the same computation, it's exactly the same trick as before. So I'm going to get the unbiased estimate as before, and I'm going to get the same thing. All right, this I can write it directly, 1 over Qt of I. So what did I gain here? I must have gained something, right, with respect to bandits. What did I gain? What's better here? Yeah, so there is more probability at the bottom. So the Q's are bigger than the P's because the Q's, first off, the Q's contain the P's, right? Q sub T of I contains the probability of I, but also the probability of the neighbors. So there's less variance than before. Cool. How can I quantify this advantage in the bound? Okay, so I see there is an advantage, but how can I quantify it in the bound? Here comes the fun part. Here comes the fun part. And so now I just redo the computation I did before for the expected regret. Everything is as before. I'm just not redoing the same the definitions. And I have the same phenomenon as before. So I go directly to the juice of the problem. So I have T sum over T, sum over I, and then I have my second moment, my second order estimates, these guys here, and I replace them with the upper bound I just computed, which is this upper bound here. Okay, I do that, and now I get the PTI divided by the QTI. So now I am wondering, what are these things? Let me write. So I want to know what is this thing, and this thing, if I write it out, is this. Okay, so listen up for a second. I have a graph, undirected, and I have probabilities on the vertices. So I'm summing up over the vertices the probability divided by the probability of the vertex itself plus the probabilities of the neighborhood. And I'm doing this for every vertex. So what is this quantity here? So there is a proof which I leave for exercise because it's a fun, you can do it from first principles. It's actually nice. So this is upper bounded by the independence number of the graph for any, so this is the independence number of G, and this is true for any PT, for any assignment of probabilities to the vertices. You guys know what is the independence number of the graph? So the independence number of the graph is the largest subset of vertices that are pairwise non-adjacent. Okay? So for instance, in this case, so the independence number of the graph, I never computed it, but it's gotta be 2, because I can definitely pick 2 vertices that are not adjacent. But any subset of 3 vertices that I pick on this graph, at least 2 of them will be adjacent. Okay? Right. So let's see, what is the independence number in a clique? It's 1. I can only pick 1 vertex. If I pick 2 vertices, they're going to be already adjacent. Okay? So alpha equals 1 for clique. Case of a graph without edges, if a graph doesn't have edges, I can pick all the vertices, and they will be an independent set. None of them will be adjacent because there are no edges. So alpha equals k if G has no edges. Okay, so now let's go back to this bound. And now we are very happy because this thing is bounded by alpha, so I can replace I can replace alpha here, and I just have to sum up over t. So what I get is ln k divided by eta plus eta halves alpha t. Now I do my little tuning game, and this is by tuning eta properly. Thank you. I was too, caught in the computation. It's gonna be alpha t ln k. Okay, so let's check. In the case of the experts, the graph is a click. So I get the bound becomes for experts, alpha equals 1. The bound becomes t ln k, which is exactly what we derived yesterday. For bandits, equals k, the bound becomes kt ln k, which is exactly what we derived 10 minutes ago. So you see, this is perfectly interpolating between these two extremes, and the independence number gives you it accounts for the amount of information that you can gather from the other, from the observational structure of the graph. The algorithm is essentially the same. Actually, the probabilities will be different because I'm dividing my estimates by different probabilities than XP3. So in this case, I'm dividing by larger probabilities my estimates because I get more observation. Okay? So this is basically what I wanted to say as far as bandits are concerned. And now, are there questions here? Yes? Can we what? Add? We mean add. Ah, yeah, I see. You can weight similarities, and you can have also directed similarities. So for instance, think of a moment like a user buys a game console. Maybe he will buy a cable to connect it to the TV. So buying one product, you can infer that he will also like some other product. But if he buys a high, XDVI cable, HDMI cable, whatever, it's unlikely that he will buy a console, no? So in some cases there are asymmetries, and this thing can be extended to take into account the fact that the graph can be directed. Numbers will be a little different, but the essence of the reasoning is the same. All right. Any other questions? No? Okay. Okay, so in the remaining 40 minutes, I would like to say a little bit about a broader picture. Okay. I believe I have, 35 minutes. Okay, 37.
So this expert case kind of approximated by what depicted by saying that on the graph
Is a click.
nodes are connected, right?
Yeah.
That would basically say that all the products are all the
Yeah.
similarity between all the products.
Everything is.
They could be completely different. We would just know it, right? So this is just a way of
Yeah.
that into the picture of the graph, right?
Yeah. So essentially means that we can infer. It's not necessarily that they're similar. They're the same. We can infer. So if it did like this, we like this half. If we like this twice. Okay.
And if we know the probabilities of all the vertices,
We know the probability of the vertices because.
it would be the same as if we could infer from one vertex to the other. So that's the same thing.
No, wait a minute. We know the probabilities. So if losses were all the same, the regret would be 0. Similarity means more. Yeah, it's more correct to say I can infer. It's not necessarily the same. Maybe I know if he liked that, he won't like this. Okay, and nice. Okay, so let's move on now. So we talked about the online learning at the beginning, and this is another question. Yeah, you can have weights. You can have weights, and you can also have probabilistic observation. So maybe you have weights, the weights on the edges represent probabilities with which you observe things. And I think can work out. Yes, there are many extensions of this. This is super easy, no? So you can add the layers. No, I did all the math. And you can prove yourself that lemma because it's cool. That lemma, by the way, tells you can view it in the following way. Assume that the probability over, I'm talking about the lemma here, which you can impress your friends. I'm talking about the lemma over here. So you can say the Pt is the uniform. If P is uniform, it's a counting measure. So essentially the lemma is saying that if I sum the reciprocal of the size of the neighborhoods of my vertices in any undirected graph, so I take fake Facebook graph, and I sum 1 over the number of friends everybody has. Okay, for every Facebook user, I sum 1 over the number of friends plus 1, which is himself or herself. This number is lower bounding the independence number of the Facebook graph. Okay. Yes, something. I just say the Facebook graph to be more impressive, but any graph. Okay, this is this is a nice fact. If you sum the reciprocal of the neighborhood size plus 1, then you get a lower bound on the independence number. Try to prove that. Okay, so broader pictures. The broader pictures is called online convex optimization. I'm gonna brush only through it, over it, because I don't have much time, but at least want to say something. Okay, so this is like, okay, let's look at a more general problem. Let's have our decision set. What was our decision set? So morally, our decision set is a simplex here, right? Because we choose probabilities, and then we have a random process to pick stuff from the probability. But we actually, the decision of the algorithm is learning these probabilities. So we can assume now that our decision set is S, which is any convex subset of a linear space. Okay? And this can be the simplex, but it can also be the set of all positive definite matrices with rank or norm bounded by something, right? Can be a very general, because you can define linear spaces everywhere. Okay, so now your online learning process is like that. For t equals 1, 2, blah, 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 we play we play our decision from our set, which was the probability before. Okay, we observe a convex loss, LT. So before we had our convex loss was a finite linear function because we had a finite domain. In general, it can be any convex loss. We pay, and you remember, the convex loss could be the square loss in linear classification. Okay, we did these examples at the beginning of yesterday's class. We pay LT of WT, and we update WT in WT plus 1, which still is in S. Okay? So now, in the case of experts, Wt is Pt, S is the probability simplex, and the losses are linear. Okay? You know, the expected, so this is like writing sum over Lt of I, Pt of I. Okay, it's a linear loss because expectation is a linear operator, so that what we were doing before morally is a linear loss. Okay, linear is fine because linear is complex, so okay. So experts is a special case of this more general scenario. And now we can define the regret. So the regret RT will be sum over T, and what you expect, right? Lt of Wt minus Lt of, minus, okay, min W in S of, sum over T, 1 over T, Lt of W. Okay, sorry, it was a little messy. It's just before we compete with the best action in our class. And we look at the cumulative loss of our algorithm. So now, how is before? Okay, before we had, you remember we had in experts, L is linear, S is a simplex. If I minimize a linear function over, so a sum of linear functions is a linear function. If I minimize a linear function over the simplex, this is always going to be minimized at the corner. So that's why this is still a special case. If you want to choose the best, if you want to compete against the best probability in the simplex against the linear loss, we're going to end up in a corner. So we actually compete with the best coordinate, which means the best action. So this is again against experts, is again a special case of what we had before. Okay, so I'm competing with the best action in the space, but this is actually, and experts is still a special case of that, because I'm minimizing linear function over a simplex. Okay, so what kind of algorithms can I expect, can I use here? So maybe I can use something, some of the ideas already had for experts case or for the bandits, right? So the first idea is called follow the leader. And I already mentioned this at the beginning of the first class. And this means that I go like that. So I always pick the one action in my space that looks best, given what I observed so far. But actually, it is easy. I won't go into the construction, although the construction is not hard, but it is easy to construct S and L1 LT such that FTL has linear loss, linear regret. Okay, so I'm not going to the construction, but this is doomed to fail. You need a bit more complicated. So the problem is that if you always go with the best, essentially the adversary can construct a sequence of losses that makes you swing from one extreme to the other extreme. So essentially, follow the leader is not a stable algorithm, and you know that stability is key in learning. You can only learn to the extent that their algorithm is stable. And this is stability, if you like, is protection against fitting in statistical learning, and is protection against linear regret in online learning. Okay? So how can we make the algorithm stable? We add the regularization, and you do this in statistical learning, and you can also do that in online learning. And adding regularization is something that you know is being studied very well in optimization. So this is called now follow the regularized leader. Funny names. Okay. So follow the regularized leader is very simple. It says that I am adding, I'm doing as before, but now I am adding a term which stabilizes my algorithm. Okay? So I have a trade-off quantity, which is a learning rate, eta. I have the same thing as before. And then I have a regularization function. Okay? This looks like support vector machines, if you like, where this is the hinge loss and this is a squared norm. And I want this function to be strongly convex. This is the right type of regularization that I would like to have. So let me just quickly define. So a function from my decision space to the reals, it's a regularizer. I call it beta strongly convex, okay, with respect to a norm. Strong convexity is defined always with respect to a certain norm, and the norm can change from a regular to a different one, if and only if for all u and v in my decision I have the following. It's like a second order Taylor expansion in which I am replacing the second order term by something okay, and now the second order term is the norm times the coefficient. Okay, so this is strong convexity, and you know there are many strongly convex functions. For instance, this function here is one strongly convex, sorry, this is the Euclidean norm, is one strongly convex with respect to Euclidean norm itself. So half the square of the Euclidean norm is a strongly convex function with the Euclidean norm, and if you plug this function here, you get equality. It's very easy to check. Another more interesting thing that brings us to our argument, to our hedge thing, is that the entropy, so this is, let me write it as phi p equals sum over I pi ln pi. So this is minus the entropy, right? Because the entropy is concave, so I have to take minus to make it. And this is actually strongly convex, is one strong convex with respect to the one norm. So it satisfies this inequality over here with respect to the one norm, with beta equals 1. Okay, why is that interesting? All right, now we can actually look a little bit how we can, for instance, recover hedge from this formulation. So now I'm going to show you that hedge is a special case of this algorithm. The algorithm that minimizes a regularized loss. Okay? So I do that is in two simple steps. First step is a trick that exploits the fact that losses are assumed to be convex. Okay? and this is called the linearization trick. So linearization trick saying, okay, I'm using convexity of the losses. So you remember we are interested in the regret is the sum of these terms. So we want to bound the loss of our respect to the loss of some u star. And u star is the, let's say, u star of t. So we keep in with the previous notation. So this is the best decision in our decision set, okay, up to some horizon big T. So the sum of these quantities makes up the regret. So now how do we work here? Okay, we can definitely use Taylor's theorem and exploiting the fact that these LTs are convex to write it like that. Okay, LT of WT transpose WT minus U star T. Okay, this is just convexity. I'm dropping the second order term, and by the way, because I wrote it in a certain way, I know it's negative. So I drop the second order term and I get an upper bound just by using Taylor's theorem in convexity, nothing fancy. So now I can call this, let's call it, to be parsimonious, we call it nabla T. And now I can rephrase the algorithm I had before, replacing the losses with linearized losses, because this makes it easier to solve, okay? So here, okay, how can I, this is hard to solve, but maybe it becomes easier if I replace these losses with linearized losses, okay? Because I know I can upper bound the regret terms with these terms here. So I can pretend losses are linear and have components the components of the gradient of the losses upper bound this difference here. I can actually rewrite the algorithm and then pretending that these are actually linear losses. Okay, so I'm faking this because these things I can compute. I have the loss. I know the loss. I can compute the gradient at every time step. And using the gradient, I can pretend that these are linear losses. So this means something very simple. This means simply that I'm using the same algorithm as before, but now I'm replacing the losses with linearized losses. And everything else is unchanged. Okay. Okay. So now I'm saying, okay, this is a linear loss. This is a linear loss because, this difference is upper bounded by that difference. So I can pretend that these are linear losses. I can compute those because I have access to losses. I can compute the gradients of the losses. Okay. So the algorithm will be reminiscent of gradient descent. And indeed, we will recover gradient descent as a special case, online gradient descent as a special case. Works, it's very easy. So let me introduce a shorthand. And the shorthand is this. So I'm just introducing a notation. Okay, I'm calling this thetas. Now I can write this as an argmax of theta t plus 1 transpose w minus that. So I swap the signs. So this contains a minus, and this plus has become a minus. So that's why I swap the argmin with an argmax. But other than that, everything has changed. So the solution will be the same. Okay? The argmin will be the same as the argmax. So now this thing has a closed form solution, and you can study this in convex optimization. Okay? And the closed form solution of this is equal to the gradient of this guy here, evaluated at theta t plus 1. Okay, this sounds a little bit mysterious. What is that? Okay, so this function is a parent, is like a relative, it's not a parent, it's a relative of the function of the regularized, and is actually the convex dual of the regularized. Okay? Let's see. Okay. So this of phi. Okay, and I can compute, you give me a regularizer, for instance, the entropy, I can compute the convex dual. There are books that tell you how to do so. Who asked the question? What? I go, no, so the gradient is going to be the arg max, but you know that if the derivative of the max becomes an arg max. This is something that, it's good to know. Okay, yes, it's true. Okay, so now, is this an algorithm? Yes, it is an algorithm. Guys, let's look at the algorithm. The algorithm is called online mirror descent. Also known as, like, follow the regularized linearized losses. So we took follow the leader, we added a regularizer, we replaced the losses with linearized version because we can, because losses are convex, so upper boundary regret with the linearized regret. And then we observed that using convex duality, we can actually write the prediction as a closed form. So now we write an algorithm, and then we look at the special case of the entropic regularizer, and hedge will pop up. And this will be the climax, and then we'll be done. Okay. All right, so how do we do here? So at the beginning, so you see these things, these quantities here are just accumulating gradients. They just take gradients and multiply gradients. These are gradients of losses. So they look like gradient descent, like. Okay, so we start at the beginning, our gradient accumulator is 0. So we are in d dimension. And now, what happens? Something bad because I have a little space here left. But so we play Wt equals the gradient of the convex dual of our regularizer evaluated at the cumulated gradient. So this is what I wrote here. It should be consistent. Yes, it is. And we pay the loss of that decision. Play and pay. Then we observe or compute the gradient of our loss. So we assume we can, we have access to the loss function in the sense that an oracle gives us the gradient of the loss at our decision. So this is our full information kind of assumption. And then we update our decision. We do the update. We know how to do the update. We just have to update the gradient. So theta t minus eta gradient of t. Okay, we just accumulate one more gradient in our accumulator. This is really a gradient step. So here we do gradient descent, but we are not using the thetas to make our prediction, but we use this guy, and this is called the mirror step. So what is this mirror step? It's telling us that you shouldn't be using the gradients themselves, but you should distort the gradient using this map. And the map is given by the gradient of the dual of your regularizer. Oh my God, yes, that's it. So let me give you two simple examples of this algorithm. I'm not going to do the analysis because I don't have time, but I will give you two simple examples. One example is this online gradient descent? It's like stochastic gradient descent. I pick a point and I make a gradient step. Is there a regularizer in this mess that gives a vanilla gradient descent? Yes. So if the regularizer is the standard if this thing, okay, so the dual function of the convex dual of that is the same because the squared Euclidean norm is a self-dual. And the gradient of this thing, you can compute it. It's not easy to compute the gradient of that, and is actually equal to that. All right. So if I use this regularizer, it means then essentially Wt is equal to theta t, which is equal to minus eta sum S1 to t minus 1 of the gradient of past losses. So this is online gradient descent, which corresponds to stochastic gradient descent when I draw losses from a bunch of examples. I draw an example, I build the convex loss associated with that example, I give it to my algorithm, and if I'm using this regularizer, I do gradient descent, just because everything becomes trivial, everything trivializes. So there's no distortion. The map of the gradients just maps the gradients to themselves. Nothing happens. But now let's see what happens when I pick an entropic regularizer, and this will be the end of everything, just to give you some incentive. So entropic. Okay, the entropic regularizer, I work in the simplex now. Okay, cool. So P is in the simplex, right? Okay, so let's do the convex dual. All right, this is a little tricky, but the convex dual, I will compute it for you, and it boils down to this thing over here. Okay, you have to believe that. Now let's compute the gradient. Oh, I know I compute the gradient. So the gradient of that is, let's say the ith component of the gradient. Okay, I take the derivative of the log, which is the reciprocal of the algorithm, of the argument. So it's the sum over j e to the theta j. And then the derivative of the single exponent, which is the exponent, e to the theta I. Oh, this, you remember, this is my Pt. All right, this looks like a normalized exponential weight. Yeah. Sum of the gradients Ls, Ps. Okay, this is the ith component. So now, what happens if I actually run this thing with truly linear losses? So if Lt of P is truly equal to a linear loss, okay, now the ith component of the gradient is going to be equal to the ith component of the loss, ls. Okay, so for linear losses, the theta t are equal to theta t of, this is I, sorry, theta t of I are equal to minus eta sum S1 to t minus 1 Ls of I, which is exactly, when we put them back over here, we recover hedge. Okay? All right. Questions? I'm a little scared. Okay, you are too tired to ask questions. Good. Okay. So what is this? Basically, we saw that we saw exponential weights that are useful to model a very nice and crisp sequential decision process. The sequential decision process can be generalized to cases in which you have partial information, which model well recommendation scenarios, settings. But actually, these exponential weights can be viewed as a special case over a more general predictor, which is called online mirror descent. And this more general predictor can be used to solve a more general class of online learning problems that are characterized by convex decision sets and convex losses. Okay? In the special case of experts, the decision sets are the probability simplex and losses are linear. But in more generality, we can do online learning over matrices, over many different objects, as long as these objects can be viewed as elements of a linear space. Okay? And choosing different regularizers will change the geometry of our gradient descent. So this online mirror descent is morally a gradient descent algorithm, but we can change the geometry of the space by choosing different regularizers. If we keep the standard geometry, this amounts to choosing the Euclidean regularization. But if you choose more exotic regularizations like entropy, we get very different things. It's like we put the gradients at the exponent, and everything becomes multiplicative instead of additive. But we can choose completely different, the regularization can change over time. So actually the regularization can also depend on the data we observe. So we can actually make the regularization data dependent, and we can arrive at second order online algorithms that have fancier properties. Okay, but I'm running out of time, and you're definitely well done for today. So I thank you for your attention, and I will give you scanned, nicely written things if you still have any energy left after you're done. Thank you very much.